Hello there and welcome back to this video series on control systems. Over the past few videos, we have defined what is frequency response. We have seen that there is what we call a polar plot and a Bode plot. We have seen this Bode plot for a first order system and a second order system. Likewise, we have seen the polar plot for a first order system and a second order system. With that, we begin by looking at what we mean by Nyquist criterion, and we'll see how this originated as an application of complex number theory to the problem of control systems. To begin with, we'll see a little bit of nomenclature, what we mean by open loop transfer function, closed loop transfer function, poles and zeros. All this Nyquist criterion originated as an application of complex variable theory to control systems area, and it became very popular. In the beginning, it may appear complex. Yeah, it really is complex because it uses a lot of complex numbers. And it may appear kind of esoteric and vague, but over time we really appreciate the beauty of it. As said, we will look into several terms that we use and add clarity to the concept. Let us say you have a negative feedback system as shown here. GS is the forward path transfer function, HS is the feedback path transfer function. For this system, we saw what is the gain from what is the transfer function from RS to CS, that is CS over RS is GS by 1 plus GS HS. If you equate the numerator to 0, you get closed loop zeros. If you equate the denominator to 0, you get closed loop poles. Because this loop is closed, we call it closed loop zeros and closed loop poles. Whereas on the other hand, you have this transfer function GS-HS, which very many times we represent as Fs, and 1 plus Fs, we call it delta S, as we are going to see later. But of course, this is all terminology that we need to remember. This is called open loop transfer function. The numerator equated to 0 gives open loop zeros. Denominator equated to give poles of open loop transfer function. As we're going to see in the next slide, this denominator of the closed loop transfer function equated to 0 is called characteristic equation and is often represented by delta of S. We are going to see that we use two different graph sheets, one to plot S, one to be called S plane and another to be called delta S plane. So this 1 plus Fs is equal to 0. So substitute the value of Fs. We have written here Fs is equal to Ns over ds. Okay. If you substitute that, you get ds plus Ns over ds. And this numerator equated to 0 are zeros of delta S, which are exactly the same as roots of characteristic equation. On the other hand, look at the denominator. Denominator of this delta S are poles of delta X, which are open loop poles. Because you can see, you get these poles of delta X by setting ds is equal to 0, but the same ds is equal to 0 gives open loop poles. So we need to carefully remember poles of delta S are same as poles of Fs, and zeros of delta S are same as the roots of characteristic equation. When we try to apply the Nyquist criterion to the problem of stability, we plot this delta S for a particular series of values of S. This Nyquist criterion uses the concept of a particular curve either encircling a point or enclosing a point. We'll try to see what we mean by encircled and enclosed. That's what exactly we are going to do in this coming slide. Let us say you have an S-plane with real and imaginary axis. This is one just graph sheet on which we drew a path. That is, we started walking along this path. That is, S is taking different values here. Maybe S1, S2, S3, S4 and so on. It is going along this path and coming to the same point. That's what exactly we are doing. Starting at a point, walk along and come to the same point. This is what we call a closed path, and we represent this by capital gamma with subscript S. This subscript we are using to indicate that we are drawing this in S-plane. Okay. We say that this point A is encircled by this closed path because it is found within this path. Whatever applies to this point also applies to this point, this point, this point, this point, this point, and just about any other point. So we say that this entire region is encircled in counterclockwise direction. If you can see, if you are walking along, you are walking in counterclockwise direction. So this point A and the entire region within it is encircled by gamma S in counterclockwise direction. Similarly, if you put the arrows in the opposite direction, we call it clockwise direction. The point B is not encircled by this gamma S path because it is not found within this gamma S path. Very quickly get used to this notation, S-plane and gamma S path. If you use delta S-plane, gamma delta path and so on. Nyquist criterion also uses the concept of enclosed. If you have a closed path as shown over here and you have a point, we will say that a point or a region in S-plane is said to be enclosed by the closed path gamma S if it is found to the left of the path when the path is traversed in prescribed direction. That is, assume yourself standing on this curve and you are walking along this curve. If you find this point A on your left hand side, you say that this point A is enclosed. If it is found on the right hand side as it is shown in the point B here, this B is not enclosed. A is enclosed and this whole region is also enclosed. We will see the second scenario here. This is the same as plane. You have 2 points P and Q. The point P is not enclosed because if you are walking along this curve, this P is found to your right hand side, so it is not enclosed. Whereas Q and the entire hatched region, they are enclosed by this S path gamma S. This Nyquist criterion also uses the concept of number of encirclements. How many times a curve is encircling a point. We'll try to clarify that as well. Let us say you have a path gamma S going as shown here. Just follow along this graph and see that it is a closed path going all along here and going all along here and coming back to the same point. For example, you have a point P as shown here and you want to see how many times this gamma S path is encircling P. Okay. To do that, from P, draw a line all the way to cut all the segments of the graph. So we draw a line here. You can see at this point of intersection between the line and the graph, it is appearing to go in counterclockwise direction. Similarly, at this point of intersection, it is appearing to go counterclockwise direction. So we say that this P is encircled twice by the path gamma s in the counterclockwise direction. Whereas the point Q is encircled by the curve in counterclockwise direction only once, because there is only one point of intersection. To get a feel of this Nyquist criterion, we need to begin with the principle of argument. It is here that you need to carefully notice the terms we use. I'll try to highlight each one. The underlined terms are key terms. I'll try to go over them one by one. We say let delta s be a single valued rational function that is analytic in a given region. When we say analytic, it is kind of well behaved. You have a definition of analytic, but let us say it is well behaved and it is defined at all points in S-plane except at a finite points. Typically these finite points are the poles of delta S. Suppose that an arbitrary gamma S path is taken. Okay. This path is taken and we are interested in the single valued function delta S, that is characteristic equation. Okay. So in S-plane you take real axis and imaginary axis, and then suppose that it is analytic except at a finite points. That is, at these finite points it may go to infinity, but at all other points it is finite. Then a path gamma S is chosen. Okay, what is this gamma S path? How to choose it we'll see later. But for now, let us say gamma S path is chosen, and this delta S will have certain zeros and poles. Let us say delta has these poles and zeros, and the path we have chosen encircles only a few of them. For example, in this case, it encircled 4 zeros, 1, 2, 3, 4, and 3 poles, 1, 2, 3. These are the poles that are encircled. And then corresponding to each value of S that you take here, that is, you take several points, S1, S2, S3, S4, and so on. For each value, you find what is delta S. Let us show that, what we mean by mapping. Okay, this S1 is there. Substitute S is equal to S1 to evaluate delta S1, locate a point. Similarly, take another point S is equal to S2, write delta S2. Then S is equal to S3, find delta S3, and so on. For several points on this path, you evaluate what is delta S1, S2, S3, and so on, come all the way back to S is equal to S1. Join all these by a smooth curve and you get what we call gamma delta path. Okay, this we drew a smooth graph all through this and we call it gamma delta path, and we say that this graph sheet on which we drew, we call it delta S plane. Okay, and they say this delta S plane path gamma delta will encircle the origin as many times as the difference between number of poles and zeros that are encircled by this S path. So we choose a path, identify how many poles and zeros are encircled in this, draw this path, how many times this is encircled, and that number of encircled is Z minus T. This we try to use as an application to control system stability, and we'll try to see that this Nyquist criterion is quite useful. So we choose a gamma S path, and then number of times the poles of delta S are enclosed by gamma S path. This is the same as the number of times the poles of open loop transfer function are enclosed by gamma S path. Then draw the gamma delta path count the number of times the origin is encircled by gamma delta path, and number of zeros, that is the number of roots, is given by n plus p. We want this n plus p to be 0 if the system has to be stable. To sum it up, we have defined several terms and what are the variables and what do we mean by S-plane, which is a graph sheet, delta S-plane, another graph sheet. You have gamma S path, is a path chosen in S-plane, gamma delta path, the path corresponding to gamma S path, and so on. And we specified what is the principle of argument. Later we will see how this esoteric kind of esoteric principle of argument can be used to the problem of stability of control systems. I think that's all we have for now. Have a great day.